live session. And Martin Baes from Oxford will talk about groups from non-expansion in higher dimension.
Okay, so thank you very much. Always nice to be at the G2M. This is my first time at one without Zoe. Won't be quite the same, but I'm very glad to see that it's continuing. So I'm going to talk about this project which we've been working on for a while now on non-expansion in higher dimension and getting groups. So this is some project I've been working on with Tingsheng Zhou in particular, and also in earlier stages with Jan Dobrovolsky. Write their names. Okay, I'm going to try to give an overview of what we're aiming for and what we know. So let me start the story with a result of Alekesh and Ronyai, which considers a, well, one way of stating it is we have a function, a rational function over the complex numbers and two variables, and say such a function is non-expanding if we can find arbitrarily large finite sets to go in for x and y, such that the image under F doesn't grow very much with respect to the sizes of A and B. But let me state it more precisely. It's non-expanding if for all positive eta, we can find arbitrarily large finite sets A and B of complex numbers such that, in terms of cardinality, yeah, such that if we look at the image under F, so this is all the possible values of F applied to elements of A and elements of B in respective coordinates, if we can find such things such that this is less than the cardinality of A to the 1 plus eta, okay? So we can arrange that it doesn't grow in terms of this exponent. Okay, so one way this can happen is if F is, for example, addition, f of x comma y is x plus y, and we take A and B to be the same arithmetic progression. Actually, sorry, I just remembered I missed an assumption here. If we're dealing with this in the original setting, I should assume they have the same size. So assume A and B have the same size. I'll say later about relaxing this, but yeah. Yeah, okay, if you took B very small, then of course you will get this. But yeah, take A and B the same size. Okay, so yeah, you can achieve non-expansion with arithmetic progressions, similarly with geometric progressions, with F being multiplication, f of xy is x times y. And the result of Alekesh and Ronyai says that that's essentially the only way you can have non-expansion. So this is the result of Alekesh and Ronyai from 2000, which says that F is non-expanding if and only if either it is addition, possibly twisted by some unary rational functions, so it's of the form g of h1 of x plus h2 of y, where g, h1 and h2 are just rational functions in one variable, or the same thing but with multiplication. That's that. xy is g of h1 of x times h2 of y. Okay, times. Okay, and these such things will be non-expanding by taking arithmetic or geometric progressions and twisting them by these unary functions. Okay, there's a corresponding version for polynomials. If you assume this is a polynomial, then these will also be polynomials. The original version was the reals, and then you need a third case in the rational function version, but okay, this is correct with the complex numbers. Okay, so roughly what I want to aim for, what I mean by this title, is a a version of this where we, instead of considering single complex variables x and y, we allow, say, x and y to range over some algebraic varieties of arbitrary dimension. That's roughly the aim. I'll say, give some precise statements very soon. Okay, so before I give further statements, I want to make one step into abstraction, which I hope won't be too shocking to this audience, which is to work non-standardly with pseudo-finite sets rather than finite sets. So here it's not too bad, but as we go further, things become increasingly awkward if we persist in really talking about finite sets. So for the statements and even more for the proofs, I want to switch to pseudo-finite sets. So, okay, so let's take U, a non-principal ultrafilter, just over the natural numbers on omega. And let's work in the corresponding non-standard complex field, so the ultra power of C, I'll call it K. So let K be the ultra power along U over the complex numbers. I'm going to think of it as a field in particular. And I want to consider pseudo-finite sets, so we say a subset of K is pseudo-finite, or strictly pseudo-finite. So pseudo-finite, and I'll write PSF as a subscript. If it's infinite, but it's a ultra product of finite sets. So it can be written as ultra product of finite subsets of the complex numbers. Okay. And I'll also do the same for powers of K and so on. A is a subset of K to the n. I'll say it's pseudo-finite. It's an ultra product of finite subsets of C to the n. And it's infinite. Okay. And then we have a natural notion of the cardinality of a pseudo-finite set. So the cardinality is the element of the ultra power of natural numbers we get by taking the cardinalities of these finite sets AI. So this will be a non-standard natural number. Okay, and then I really want to get at these exponents, so I'm going to make one more definition. If B is another pseudo-finite set, let's define delta with base A of B to be the standard part of the log with base the cardinality of A of the cardinality of B. Okay, so standard part is in the closest real to this non-standard real, if it exists, or infinity if it's too big. So this is a non-negative real, or it's infinity. So e.g., if I take A squared, A times A, with respect to A, that will have delta 2. Okay, this is the coarse pseudo-finite dimension with base A. Okay, good. And now in these terms, I can re-express f being non-expanding. So f as here, f a rational function in two variables. F is non-expanding now, if and only if there are pseudo-finite A and B in this non-standard complex numbers K, such that they have the same cardinality. And delta of f of A comma B, which makes sense, just apply this rational function f at these on these sets with respect to A, is 1. Okay.
And f is over K? Or
F is still over C,
over C?
I mean, I could consider f over k as well, but okay, in the settings over C, which is a subfield of k. And yeah, this extends the complex numbers by the diagonal embedding. Yep. Okay. Okay, so that's a pretty straightforward translation. Yes. Okay, so now I want to. Sorry, any questions on this so far? Okay, so now I want to start talking about the higher dimensional situation. I guess I want to start by stating two existing quite strong results in this direction, and then talking about what's missing. So the first is a result of Green and Tau, which is really about approximate subgroups of algebraic groups, of linear algebraic groups in characteristic 0, but I'll express it in these terms, or consequence of it in these terms. So let G be a complex algebraic group. Okay. And I want to consider non-expansion with respect to multiplication. So suppose, in these terms, suppose we have pseudo-finite subsets of the group. Okay, so now I'm taking the k points of G. And suppose that it's non-expanding in the sense that delta of A times B with respect to A is 1. So by multiplying, we haven't really grown. And let's still assume some symmetry, saying B also has delta 1 will do. Okay, so B has the same cardinality of A. That holds. This is just slightly more general. Okay, this is the key thing, non-expansion. Okay, then this result on approximate subgroups yields that A concentrates on, and I'll see what I mean, a coset C of a nilpotent subgroup of G, nilpotent algebraic subgroup of G. Okay, so what do I mean by concentrates on? I'll say that A concentrates on, well, a constructible set in general. But C in this case concentrates on C. Just means that we haven't lost anything if we restrict to C as far as this is concerned. So as far as delta is concerned, so delta of A intersects C with respect to A is 1. Okay. So it has large intersection with C in this sense. Yeah, okay, so nilpotent here, you can see the analogy with these abelian groups coming here, or think of it as generalizing that. This is a rather more specific case, we're just in a group. In other words, if G is not nilpotent, then you don't get these non-expanding sets, which are really well, in general position, in a sense, in the group. So dense, and not just in the Zariski sense, but in the sense of concentrating on G. So it has to be something nilpotent where they concentrate. Okay, so that's one result. Another is the work of Elekes with Szabó. Szabo. So, okay, I don't want to state this in complete generality or precision, because it will get us a bit away from what I want to talk about, but let me say at least a slightly special case. So V is an irreducible algebraic variety. So now we're not talking about a group, just an arbitrary variety. And we have, let's say, a function from V cross V to V. So this is looking like a higher dimensional generalization of what I had here. And this could be a rational function. It could also be something more general. Let me say finitely valued. Of correspondence in the coordinates. Let me not say precisely. And with some non-degeneracy condition. Really depending on both coordinates. Okay, so then the result of Velikovsky-Szabó implies, actually, again, it's more general really, that if we have non-expansion here, then it's because of an abelian group. So let me state this slightly precisely. Sorry, but with a key assumption. So suppose we have A and B, pseudo-finite subsets of V, and suppose that they're in general position in the sense that if I take the intersection with a proper subvariety W of V, then it's finite. Okay? So if A intersect W and B intersect W are finite for all proper subvarieties of V, for lower dimensional subvarieties of V. Okay? So this is, saying that it doesn't concentrate at all on proper subvarieties. Barely. Okay, then it works. So I'll call this general position, this assumption. A and B are in general position in V. And an expansion. Let me put it here, delta of the image of A and B under F with respect to A is 1. Okay, and this general position assumption. Then we get that it comes from a group. So, yeah, okay, I decided not to give a precise statement, but up to some finite-to-finite correspondences in the coordinates, F is just addition where? In some group. So for some G, a commutative algebraic group. Okay. Let me give credit. The fact that it's commutative came later. That was first observed by Emmanuel Préard and Hong Wang. Is it legible? Okay.
And also delta A of B is equal to 1, or like?
Yeah. Yeah, the same non-expansion assumption. Delta of F of A comma B is equal to 1
yes,
with respect to A.
The size of B with respect to
Yeah, sorry. Thanks. Yeah, sorry, same symmetry assumption, indeed. I ran out of room. Sorry, yeah, delta A B is equal to 1.
Okay.
Yeah, thanks. Sorry. Yeah. Okay, so that's what I want to say. So this is a nice, quite general result, but this assumption is very strong. It's a general position assumption, and in particular, you can see it's ruling out some cases which do occur. So we're only getting abelian groups here, but in general, you should get nilpotent groups. So the point is, if you do this with multiplication in a nilpotent algebraic group, then the approximate subgroups which witness non-expansion won't be in general position, because they will concentrate non-trivially on commutator subgroup in particular. So basically, what we've been aiming for is a common generalization of these two. So something which will remove this assumption, and the conclusion will be nilpotent groups rather than just commutative groups. Okay. So my plan for the rest of the talk is to give a concrete, quite simple special case of that general conjecture, which I won't state precisely, though we have precise statements, and tell you about our progress towards proving it. Okay. All right, any questions? Good. Okay, so to go towards what I want to talk about, I need to rephrase or look at things in a slightly different way. So this symmetric assumption we have always, so the fact that this is v cross v here, that we've got the same variety in both coordinates, or same dimensions, and also this assumption here that b has essentially the same size as a, these become too strong and not really the right thing when we start to talk about these generalizations that I'm aiming for. So if you think about nilpotent groups acting on sets with non-trivial stabilizer, that will be an asymmetric version. So I want to go to an asymmetric formulation. So yeah. This will turn out to be fairly neat, I think, once we get it going. Okay, so to motivate, let me return to this original case of the allocation on the I. So suppose f, again, is a rational function in two variables, non-expanding, witnessed by some sets A and B, pseudo-finite. As over there. So I can view this slightly differently. I can think of these B's as parameterizing a family of unary rational functions. I plug in elements of B for Y. So let me do that. So consider F the set of rational functions in one variable. For B and B, ignoring the finitely many B's there may be, such this doesn't work. So this is going to be some set of rational functions in one variable x, and moreover it will be of bounded degree. So there'll be some bound on the degrees of these rational functions, which is the degree of this f in x. Bounded degree. Okay. Okay, and this non-expansion condition that delta of f of a comma b is 1 then becomes that delta of capital F of a is 1. Right? Well, I mean, take all the things in f and all the things in a and apply the things in f to the things in a. Let's see the finite subset here. Okay, so now things are looking less symmetric, and this suggests how to generalize. So generalization allow such f, which are pseudo-finite subsets, or pseudo-finite sets, of rational functions, let's say v to v for v some variety, and with some bounded complexity, corresponding to the bound on degree here. Okay. And actually, I will simplify things for this talk and only talk about birational functions, which doesn't include the full case here, but is already difficult. So let's just restrict to birational functions. Okay, so let me then give, I'm going to give a precise statement here. So now I'm taking V, an irreducible variety over the complex numbers. And we can consider the group of all birational maps V to V. So rational maps with rational inverse. So this is a group under composition. It's far from being an algebraic group in general, but all I'll need to say about it is that we can write it as a union of constructible subsets where we bound some notion of complexity. So we can have some notion of complexity of a birational map such that every birational map has some natural number complexity, and the sets of bounded complexity are constructible. Okay. So in this case, we took bound on degree. Doing this in a nice geometric way is tricky, but for our purposes, we can just be very naive and say that the complexity is the smallest length of an ACF formula which defines the map. That will work nicely, actually. So this is, okay, in a way this is in the background, but let me mention this is what's called an inconstructible group, an indefinable group in ACF. So the point is that if I take compositions of things of bounded degree, so things of birational things of degree less than d, inverse times things of birational degree less than d, then this will be of bounded degree. This will be contained in things of degree d prime, where d prime depends only on d. Okay, so it's this union of constructible sets where when you multiply things in sets at one level, you get up to just some bounded higher level. Okay. Right, maybe that's not going to be explicitly important. Okay, so now I want to state the conjecture. Let me delete something. I guess this. Okay, I'll call this conjecture 1. So this was okay. This is a special case of something we came to in a paper with Tingsheng. So okay. So here's the statement. So suppose I have V is here, just an irreducible complex variety. I have a pseudo-finite subset. So it's in VK. And suppose it's really that the V is the right thing to consider for A in the sense that this doesn't concentrate on any proper subvariety. So it concentrates on no proper subvariety W of V. Okay, this is a pretty weak assumption. And suppose we have a pseudo-finite set of birational maps of bounded complexity, less than some d, which is not too small. So now I'll make a pretty weak symmetry assumption, just that delta of f with respect to A is greater than 0. And suppose that we have the same non-expansion condition, delta of fa with respect to A is 1. Okay. Same kind of non-expansion. Then what we expect is that f, same as in the BGT thing, that f concentrates on a nilpotent algebraic subgroup of the birational maps. Okay. Okay, so as I said, this is typically not an algebraic group, the set of all birational maps on a variety, as soon as the dimension is greater than 1. But it can have algebraic subgroups. They tend to be quite constrained, and the nilpotent ones even more so. Okay, so once we know this, we can then work out what the nilpotent algebraic subgroups of this are in a particular case, and then get to something like the original Alekesh-Ronyi result. Did I miss something?
No, that's okay.
Is that okay? Clear?
Yes.
Okay. Yeah, any question on that statement? Okay, so this is a conjecture. Let me make a couple of remarks to make it more plausible this is the right statement. So firstly, well, we can delete this nilpotent by this result eventually. So yeah, if we can prove this, if we can just prove that we get down to an algebraic subgroup. Oh, coset, I missed coset. Sorry, F concentrates on a coset of an nilpotent algebraic subgroup. Okay, sorry. Yeah, so if we can just get that we get down to a coset of an arbitrary algebraic subgroup, then, well, it will be nilpotent. And the other point is that we can't strengthen this, we can't get better than nilpotent here. So kind of sharpness was something we proved with Dobrovolsky and Zoe in 23 on arXiv, which is that, yeah, we can't strengthen nilpotent. We need to allow arbitrary nilpotent groups here. For example, yeah. Yeah, you need to allow arbitrary nilpotent algebraic subgroups of this. Yeah. Yeah, but because any such, you could take V to be the group itself if you take an arbitrary nilpotent algebraic group, and then you do get examples which do concentrate on the whole group.
So, but just a question, in the original examples, the maps are not birational, I mean, these are only rational.
Yeah, yeah, indeed. So this is not, as I've stated it, this is not a strengthening of the original Alekesh-Ronyi statement.
Okay.
Agreed?
Yeah, okay.
Although, okay, I'm about to say results towards it do generalize the original Alekesh-Ronyi one. Yeah, but okay, so if you replace birational with rational, it's not a group anymore,
Yes.
and it's not, you don't get such a nice, okay, I'm not sure what the correct nice statement in that setting is.
Okay.
Yeah, okay. I tried to work it out before this talk, but I failed. So. And I think our general conjecture will imply something nice, but yeah, I'm not sure exactly what statement. Okay. So let me say some things. Well, firstly, is if we do consider the original setting of Elekes-Ronyi, where V is just the line, well, then it's not so interesting because the birational maps, it's already an algebraic group in this case, it's just PSL2, Möbius transformations. But this is still saying something. It's saying you get down to the nilpotent subgroups of this, which are just abelian ones, conjugate to upper triangular or diagonal, correspondingly additional multiplication. So this fits with the Elekes-Ronyi result at least. Okay. And actually it's true in this case. Something more general is true. Okay, so let me tell you some results towards this. If there's no question.
What is ER?
Oh, Elekes-Ronyi, sorry, the original state, the first statement I wrote. Yeah, so there you got additional multiplication, and if you think about the nilpotent algebraic subgroups of this, it's additional multiplication. Okay. And there's some translation work to do between saying that and the original statement, but yeah. Okay, I want to mention 4 results in this direction. Okay, so the first is one for myself and Ting Xiang we put on the archive last year. So one, okay, it's really something stronger, I'll say something, but in particular we get that conjecture 1 holds if we add a condition like this one, like this general position assumption, but now in this asymmetric setting. So conjecture 1, yeah, if, okay, that should be constated like this, if A intersect W for W proper subvariety of V has delta 0. Okay, so barely concentrating on proper subvarieties. And moreover, in this case, again, we get just abelian groups. I didn't name the subgroup, let me name it. H, and H is commutative in this case again. So actually we proved this, so full result here, I won't go into it today, but full results, it strictly generalizes this ES result, so it's not just for birational maps, and it also gives a strengthening of the original Elekes-Ronyi result with an asymmetric version where we replace the assumption that B and A have the same size with just that delta of B is greater than 0. Yeah. Okay, but that's not the result I wanted to concentrate on today, but I should mention it. Yeah, so this is still with this annoying general position assumption. This is only slightly weaker than that one. So we've been trying since then to really see what happens without that. And we have a couple of successes. So firstly, something from earlier this year, that conjecture 1 holds in the case of V being the plane, if we restrict to not arbitrary birational maps, that's a rather complicated group in this case, but just polynomial automorphisms. Okay, so this is the polynomial maps on A squared with polynomial inverses. Yeah, okay, I'll say more about this in a bit. But that's the statement then. So same statement, we get it concentrates on nilpotent algebraic subgroup of this group. And okay, then it's not too hard to see what those nilpotent algebraic subgroups are in this case. And so we do get a statement like the original Elekesh-Ronyai result for map for functions f of x comma y, where when we fix something for y, we get a polynomial automorphism. Okay, that's one result. So what we're hoping for is, well, this, well, maybe the next case to consider of this is V still being the plane, and considering arbitrary birational maps, so the Cremona group. This seems to be challenging, but we're getting somewhere. So one case of that we implicitly did a while ago with Jan Dobzwolski as well. So this was, okay, a pretty special case. We take V to be, well, a rational surface, so we could think of it like this, but actually I want to think of it as a smooth cubic surface in P3. Okay, so this is birational with the plane. And not considering arbitrary birational maps, because that would be the full Cremona group, but considering just some particular ones, so the Geyser involutions, which are the birational maps you get by considering collinearity on this cubic surface. So let me just draw it. So if I take a line in P3, it will intersect my surface, typically in 3 points, because it's cubic. Okay. All right, I'm very bad at drawing things, but I'm imagining some cubic surface here, and these are the points of intersection. Okay. And we consider the rational map, gamma sub A, which sends B to C. Okay. So this defines, for typical A, this defines a birational map from V to V. And if we restrict to these, and also we work there with a symmetric assumption, and maybe it's not so clear how to relax it, so assume also that delta F is 1. Okay, then conjecture 1 holds in this setting. Actually, because this never happens. And including this assumption that A doesn't concentrate on anything proper. Yeah.
So we just for the first case, automorphism, polynomial automorphism of the plane. What are the basic examples of nilpotent algebraic subgroup of A2? Are there a lot of?
Kind of. So you take elementary maps. So if you consider x comma y goes to x plus a polynomial in y, comma y plus b. Okay, and consider this for p of some bounded degree.
Yes.
and be arbitrary, that will be a nilpotent algebraic subgroup.
Okay, so this is a nilpotent subgroup.
Yeah,
Okay.
and basically, up to conjugacy, they look like these,
Okay.
or some abelian ones, some one-dimensional abelian ones. Sorry, not just one-dimensional, sorry, or some abelian ones. Yeah, okay. Okay, and I wanted to mention, I'm not sure I should, but I'm going to, that we also have some work in progress, which is not written up yet, but I'm pretty sure works. Well, and the techniques should give us much more than we have so far, but let me just say in particular, we can get it for V being, again, the plane, and considering F to be something special again. So another kind of birational map you can get is if you take a rational function in one variable, we can act on a pair x comma y by sending x comma y to x comma f of x times y. Okay. So shifting multiplicatively in the fibers by something which depends on x according to this function. Okay, so this will be a birational map. Okay, and we can handle these. So the only the nilpotent subgroups here are just cosets of the constants. And we get down to that. Okay, maybe I'll say more about that at the end if I have time, which maybe I won't. Okay, so there's a results we have so far. Okay, but we have some techniques developed to prove these, which hopefully we can push quite a bit further. But so far, each new case we've considered, we've had to develop new techniques. Okay, so if there are no questions, I was going to spend the rest of the time sketching some ideas of the proofs involved in this automorphism case, this one, and maybe also this one, if I have time. Leave the conjecture. Good. Okay, so the first step towards actually proving anything is going to be a little more abstraction again. So proof ideas. So let A and F be as in conjecture 1, satisfying all those assumptions. We want the conclusion that F concentrates on an algebraic subgroup. Okay, so to get anywhere, what we've found we can use is some technology developed by Hrushevsky of pseudo-finite dimensions. So let me try to summarize this briefly. So yeah, okay. So we work in an expansion of the field K with predicates for these pseudo-finite sets A and F. So a countable expansion, so to a countable language L, and we choose this expansion such that this delta works nicely, basically that it's definable, or more precisely continuous. Continuous, by which I mean that, okay, nice way of saying it is that if you consider the map from type space to the reals given by sending the type of A to delta of the realizations of a formula phi in K, where we put in a parameter A. Okay, so this is from the type space to the reals, extended by infinity. That this is continuous, well, and well-defined. Obvious, for any phi. Okay, so one can achieve this by iteratively adding in some definable sets, which you need to make the topology here rich enough that this is continuous. Okay, slight technicality, but that's all I want to say on that. Then what I'm going to say will work smoothly. So we now define delta of A over C for A in K, or a tuple, and C a subset, to be, well, I'm going to write the natural definition if I try to think of delta A as the dimension of a definable set, and I consider the corresponding dimension for type. So delta A over C is then the infimum of this delta with base A of phi K for phi in the type. Find the type of A over C. Yeah. So think of this as the dimension of A over C, like transcendence degree or linear dimension. And then we get a corresponding notion of independence. So we say A is delta independent from B over C. B again some tuple from K. If, well, usual thing, we could think of this as a dimension, delta of A over C along with B doesn't go down with respect to delta of A over C. Yeah, delta of A over C with B is just delta of A over C. Adding B didn't give us any new definable sets of smaller delta, in other words. Okay, and this behaves well, symmetric, transitive. And I want to make one last little definition here, which is that I want to define K0 to be the closure of the empty set with respect to this. So delta closure of the empty set, by which I mean just the points of delta 0. Okay, the elements of K with dimension 0. This will be an algebraically closed subfield. Okay. Okay, that's the setting. And then we can essentially rephrase this conjecture in those terms. So, okay, continuing to assume that we have this A and F as in conjecture 1. So satisfying these assumptions, using those assumptions, we obtain a point in A, little a, and a point little f in F, such that they have full delta. So delta A is 1, which is delta A of A. And similarly, delta F is delta A of F, what that is. So this is an upper bound because this is one of the sets in the type. But we can achieve it. And moreover, we can have A independent from F, in a sense. And then the corresponding to this non-expansion, we can also have that F of A is independent from F. So why does this correspond to this? So this is equivalent to delta of F of A being 1, because we look at delta of F of A over F, because F is birational, this is delta of A of F. You can get from F of A back to A by applying the inverse of F. So then this independence just means this. Because this is 1, so this is 1, because of this independence. Okay, so this is the non-expansion assumption in this translation. And also corresponding to this, that translates to A being generic in V over this subfield K0 in the end. So if it if it does concentrate on a proper subvariety W, you can actually get it to be over K0. So, okay, and vice versa. So it corresponds to this. And then, in these terms, to conclude what we want, so to conclude conjecture 1, we want to show that F just is in the coset of an algebraic subgroup defined over K0. Okay, or in other words, the locus of F over K0 is contained in the coset. Okay, so this is now our aim. We just want to find F in a coset. And okay, I struggled to find a way to avoid this technicality, but I failed, so let me say something just to make sure what I say next is true. We can assume, by adding some constants to the language, that A and F are algebraically independent from this K0 over the definable closure of the empty set in this language. Okay, there'll be some finite part of K0 which we need to add. And because it's delta 0, adding it doesn't disrupt anything. Okay, any questions on that? Good. So, okay, now I can basically indicate how we prove this result for the polynomial automorphisms. So we want to say next. This is F being in what I call G, polynomial automorphisms. I'm thinking of the capital K points. I don't write anything. Okay, so yeah, so there are two key things. Well, three key things. Yeah, let me do them in this order. So firstly is what we use here is that we understand the group structure of this group very well, and in a way that's not so true for even for the birational automorphisms of A squared. So namely, there's an old theorem of Jung that G is just an amalgamated free product. So it's of the form amalgamated free product of some subgroup E with the affine transformations over their intersection, where this E is the elementary automorphisms, which is something like what I wrote earlier when Antoine asked. But let me write it out. So it's in general, it's the maps x comma y goes to ax plus a polynomial in y, comma by plus c, where p is a polynomial and a, b, and c are elements of the field. So we can write this as a union where we bound the degree of the polynomial, and those will be subgroups. So ED is where we restrict to the degree of this polynomial being at most D. These are subgroups. Let me calculate it out. Not normal in G. Okay, so it turns out that G is this amalgamated free product. So the intersection, by the way, is exactly E1. It's going to be affine linear, then this should be a linear polynomial. Okay, that's the first tool. Yeah, now the next technique I want to talk about, which has been really behind most of the results I discussed earlier, is seeing how to apply the instance bounds that you get in characteristic zero fields. So by this, I'm referring to results along the lines of the Semredi-Trotter bound on point line instances. So there are wide-ranging generalizations of that, which we can use. So in this setting, what turns out to be important is to look at the elements of the group with infinite fixed set. I'll explain why in a second, but let me first just write this fact, another fact about a fact from the literature on polynomial automorphisms, which we'll need, which is that for G, a polynomial automorphism, if it has infinite fixed set in its action on the plane, okay, this is infinite, then that can only happen if G is elementary or conjugate of elementary. Okay. All right. Fact. Okay, so why am I looking at fixed sets? Yeah. Let me summarize with a lemma. Lemma 1, I guess. So in this setting, okay, with this A and this F. So it turns out that we can bound delta of F in the setting by 1 plus the supremum of transcendence degrees over F of polynomial automorphisms G, where G has the same type as F in our full language, L, and the fixed set of G inverse F is infinite. Okay, so this looks pretty random maybe. Let me try to say something about why this is the case. Yeah, so let n be the right-hand side. It's 1 plus the supremum. So assuming this is finite, it doesn't... Sorry, this is definitely finite because f has some bounded transcendence degree. But yeah, sorry. So take n to be the right-hand side. And consider the action of G, diagonal action of G on V, here's the plane in this case, on V to the n. And then what we get from this is that if we take G with the same type as F but not equal, then if we look at trying to solve G times a tuple X being equal to F times a tuple X for this diagonal action, then this has boundedly finitely many solutions if we consider generic X. Okay, because of this transcendence degree restriction, because the fixed set will be of smaller dimension, and saying this means that X is in this fixed set, right? Or each element of X, each coordinate of X is in this fixed set. So there's some drop in transcendence degree of X, so by some additivity you get a drop in transcendence degree of G. So you get this band. Okay, and now why am I saying this? Well, because this is what you need to apply these instance bounds. So this gives us that we omit K2S for the corresponding graph where you consider R to be related to, say, X, comma f of X. This omits K2S, or S, omits K2S. I mean the complete bipartite graph on 2NS. For some S, as this bound. Okay, so then instance bounds, just using some technology here, then give us, well, in the end, they give us this result. So they give us a bound on delta of a pair here, and in the end, it gives us this with some manipulation. Okay, so result. Bound. Okay. Okay, that was pretty sketchy, but so the key thing is that this is where we're using the instance bounds. Yeah, and this idea of looking at the infinite fixed sets, this was also what was behind this result on cubic surfaces. We had to use the same idea there. And, well, and probably this lemma will be useful in other cases, although we don't have specific examples we can prove just using it so far, except this one. So let me show you finally, I guess, well, let's see, how to use this. So, okay, so a sketch proof of the conjecture 1 in this case. For polynomial automorphisms. So, okay, I'm going to cheat because otherwise it would take far too long. I'm going to pretend that this is empty, okay, or trivial rather, that this is really just a free product of E and the affine. So pretend it's not true. Pretend G is actually just the free product of E and affine. And the fact that it's not true makes things awkward, but the ideas are the same. Okay, so if we pretend that, then this F we're considering, that we wanted to see was in a coset, we can write it as some alternating word in E and the affines. So let's say it's T1 times T2 times ... times Tn, alternating. So Ti is in E if and only if Ti plus 1 is affine. And each of them is either elementary or affine. And none of them is the identity. Right, I can assume that neither T1 nor Tn, the ones at the end, are over K0. Because if they were, I could just multiply to kill that term, and it wouldn't affect the result because we're looking for cosets defined over K0. And left or right doesn't matter because we can conjugate. Okay, so we can assume that these endpoints, are not in K0 for the conclusion we want. So now it suffices to show that n is 1, because that means that f, after doing this, f is just either an elementary or an affine. Why are we done then? Well, what I should have said is that we can assume that these are in ED for some finite d. So now we will get that f is in one of these algebraic groups. These are algebraic groups. And we wanted it to be in a coset of an algebraic group, so we're done. Right, algebraic groups defined with no parameters. Okay, so sufficient to show this. So suppose not. Suppose that this word is of length greater than 1. Okay, the next step, which again is something we do in many of these proofs, is to consider iterating our construction. So we have this f, which sends a to f of a. Well, we can then again apply some independent copy of f and keep going, and go back and forth applying independent copies of f, and things will become more smooth as we do that. So let's say that properly. Yeah. So now consider a chain f0, which is f, and fi plus 1, which is fi prime inverse times fi, where fi prime is an independent copy of fi over fi of a, so also independent. Okay, so draw. We have fi ascending a to fi of a, and we take an independent copy fi prime, and well, that will there'll be something here, a prime. So this composition is sending a to a prime. I'll take this independent. Okay, so this a prime will be fi plus 1 of a. Good. Okay, so the first point is that when I do this, so if we're assuming that our original f had length greater than 1 as a word, when we take a copy like this, it will have the same structure, same kind of word. So when we multiply like this, it will get longer. And they'll keep getting longer, and moreover, because of this independence, they will do so in a way which means that this delta of fi grows. So it's unbounded, in particular. This delta fi is unbounded. Okay, so this is using our assumption that the length of the word is greater than 1. Okay, we'll call this fact star. Now I'm going to contradict that. Over here. But I'm going to use this fact. Well, it doesn't matter. Okay, I'll tell you it when I use it. So now I want to apply this lemma to get a bound which will contradict this lack of a bound. So I want to consider some gi with the same type as fi. Okay, so suppose we have some gi of the same type as fi with this fixed set being infinite. Fix of gi inverse fi infinite. And I'll say we get a uniform bound on transcendence degree, as in lemma 1, which will suffice. So, okay, if this is infinite, then the fact said exactly that this must be a conjugate of elementary. Gi inverse fi is a conjugate of an elementary automorphism. And then if we consider the structure of these as alternating words, so fi, so it came from our original one by a process of composition, so it has some alternating word structure, s1 up to sk minus 1. Okay, and then the point is, the only way this can happen is if there's some elementary in the middle here, and gi is the same except there. Okay. All right. So if you do take gi inverse fi, you get whatever e prime inverse times e conjugated by this, right? No, by this, sorry. And well, playing around a bit with these three products, you see that's the only possibility. Okay, so now we're done. So, but then you can extract each of these from fi, as in they're in the algebraic closure of fi. So if we look at the transcendence degree of gi over fi, well, we have these from fi, so this is less than or equal to the transcendence degree of e prime, and we were considering always words where the elementary maps involved was degree at most d, so this is at most the dimension of ed, which is some fixed finite number, depending only on the original f. Okay, so the lemma then tells us that this delta of fi is bounded by 1 plus this, which is something fixed. And that contradicts the fact that it was unbounded. As I said there. Right, yeah. That's it, modulo the lie I made and proving that lemma. Yeah.
So the lie you made was just ignoring relations between E and...
Yeah. So, so it makes everything a bit more complicated because you have to work with cosets of that intersection everywhere, but it works in the end. Okay, do I have any time left? Oh, I could have 3 minutes or something? Or
Yeah.
3 minutes?
8.
8 minutes, yeah. Okay. Good, then let me say something about this work in progress. Yeah, okay, because I think the techniques at least are interesting. Yeah. Okay, so this was this case of KT cross in progress with Xinxiang. Yeah, so right. So I wrote up already how this can act. So this is a pretty simple kind of birational map on the projective plane. And if we want to handle the full group, then we certainly have to handle this. And yeah, let me tell you the story. So when we first looked at this, we were pretty dispirited, actually, because we observed this conjecture 1 in this case, even just for the case of a birational function of the form x comma y goes to x comma x minus some b times y, with b varying. So this is some special case of that. But this, if we can prove our conjecture, it would imply another conjecture of that we found in the literature, so of Balog, Roche-Newton, and Zelazov. Sorry, I don't know how to pronounce that name. From 2016. Okay, it's not too important what it states, but let me give it anyway because it's easy to state that for all L, there's a k and an epsilon, such that for every finite subset of the reals as they had it, if you look at iterated products of differences of A, so A minus A times A minus A times A minus A k times, and look at the size of that, then, well, it should grow. That's a kind of sum product phenomenon. And our conjecture was that it's, for all L, it's eventually greater than the size of A to the L. Okay. Okay, so it's not immediately obvious why this implies this, but I mean, basically take x and b to be from A and y to be from here, take a limit as k goes to infinity, and you get that our conjecture would imply this one. And we had no idea how to prove this, so we were a bit disappointed. But then we found, looking more in the literature, a result of Akshat Mudgal, who showed in 23 that you can prove this conjecture modulo the weak polynomial Feynman-Riescher conjecture, not conjecture 1, this conjecture. It's called conjecture 2. Which is good because this is a theorem of later in that year. of Gowers, Green, Manners, tau. Okay. Sorry, I'm not writing it out. This is the weak polynomial Feynman-Rüscher conjecture. Maybe I should write it out. So, weak polynomial Feynman-Rüscher. So maybe I won't write it, but it states that if you have, one way of saying it is if you have a k-approximate subgroup of a torsion-free abelian group, then it's contained in polynomial in k many cosets, many translates of a finite rank subgroup of rank big O of log k. So log k many, log k rank subgroup and just polynomial many translates. So that was a big open question for a long time, and they solved it. Okay, why does this imply conjecture 2? Well, the idea in Woodgall's paper was to apply quantitative versions of the subspace theorem, which I would think of as the case of Mordell-Lang for the multiplicative group, where you consider linear varieties intersect finite rank groups. And that turns out to be enough to give this. Okay, so then we thought we should use such techniques ourselves. So yeah, so what we can say using this and quantitative Mordell-Lang results, and for the best things we can say using these quite recent uniform Mordell-Lang results that I think Gareth told you about the other week, and some Balog-Samoredi-Gowers. Yeah, let me just state as a lemma, which seems rather powerful. So if we're in either a power of the multiplicative group or an abelian variety, arbitrary semi-abelian seems to be not yet solved. And this could even be over K. If we take G and A in the group with some non-expansion for addition, so in this form that A is independent from G, which is independent from G plus A, then the locus of G over this K0 is a coset of an algebraic subgroup. Yeah. Okay, so this seems very useful. And I guess I now really don't have time, but it allows us to deal with this in particular. So by considering, very briefly considering a pair of fibers for x and x prime independent, and then seeing that we get such a situation in the product of those fibers, which then gives us a multiplicative dependence, using this in the case of multiplicative group here, a multiplicative dependence, which then is basically, well, yeah, enough to tell us that not very much can be going on, and we get down to a coset of the constants. Yeah. Okay, and it seems like it should be able to do much more, but that's what we have so far. Okay, thanks.